Alright, so I want to introduce a little problem here. Suppose your phone falls out of your pocket when you're sitting in the bleachers watching a football game. You wanted to get the best view of the field, so you were sitting in the top row, which is 40 feet off the ground. How fast will the phone be falling when it's 1 foot above the ground? Rather than doing when it hits the ground, but because hopefully we'll catch it. But how fast will it be falling when it is 1 foot above the ground? Okay? Now I have a little bit that I want to look at first, and then I have part that I want you guys to explore as well. Alright, so first of all, we've done stuff like this before, where we have a falling object or a projectile of some sort. But remember the formula for the height here is d of t. We're going to write the height as a function of time. And the formula is h plus vt minus 16t squared. Okay? Now, remember that, well, tell me, what is h?
Height, the initial height.
The initial height, good. So our initial height is what in this case?
40 feet.
It's 40 feet. Okay? Plus vt. Now, what does v stand for?
Velocity.
When?
When it's falling.
Time.
Oh, initial velocity.
The initial velocity. Now, if it fell out of our pocket, what's our initial velocity?
0.
0, okay? We didn't like take it out and throw it. You know, we didn't throw it on the ground. We just dropped it, okay? So, that VT part in this case is just 0, okay? And then we have the minus 16t squared.
Wait,
okay?
VT is velocity, like...
The initial velocity, vertical in this case, vertical velocity times the time, okay? Now, if I want to find the point that is 1 foot off the ground, what would I do? Yeah, plug in 1 for d of t. Good, so 1 is going to equal 40 minus 16t squared. Okay? So if I do 40 minus 16t squared, and I solve this, we get negative 39 equals a negative 16t squared. T squared is 39 sixteenths. And that means that t is going to be the square root of 39 sixteenths, which is root 39 over 4. And if you plug that into your calculator, you're going to get it to be approximately 1.56. Okay? So that's the amount of time. That's seconds. The 1 feet, that's our y coordinate, or d. Alright, so our point F is the point 1.561. Okay? Now, just using what we know, what's another point on this graph?
The origin. Oh, 40. The origin.
Well,
Or like the initial point.
okay, what's our initial point?
40. 0.
Other way around.
0, 40, yeah.
0, 40. Okay? 0, 40. So at 0 seconds, it's 40 feet off the ground. Now, if I asked you to find how fast this thing was going, what might your initial thought be?
Gravity? 9.8 meters per second. Or whatever.
Well, that's your acceleration of gravity.
Okay.
What were you saying?
I don't know. I was going to say like average of a few of them, but I don't know. Doesn't make sense.
Okay. Well, let's think about your basic distance times time. Distance times rate equal, or distance equals rate times time.
Would it be 40 like feet per 1.56 seconds?
Okay. It's, well, not 40 feet. How many feet did it fall so far?
39.
39. So the initial speed right here, or velocity if you will, the speed is going to be that it fell, and we'll make it negative. So actually that would make it a velocity, because we're indicating direction here with that negative. So velocity is a negative 39 feet in 1.56 seconds. All right, so if you figure that out, what would that give us? What is it?
25.
All right. So negative 25 feet per second. Now, I want you guys to understand this, okay? What did we just find?
Did we find like
The
the
velocity, the speed of the object when it's 1 foot off the ground.
Okay,
average velocity?
Yeah.
okay. That is not exactly how fast it's going when it's 1 foot off the ground. That's the average speed over the whole first 39 feet of free fall. So at the beginning, you guys know how this works. At the beginning, it's falling slowly, and then gravity makes it speed up 32 feet per second every second of free fall. Okay? So we want instantaneous velocity. Okay? An instantaneous rate of change. Now, if you think about what we actually did with those 2 points, 0.40 and 1.561, what did we actually find when we found the velocity in relation to those 2 points? We subtracted the 1 minus 40, we did 156 minus 0.
The distance
So we
between
found
them,
out the velocity.
or the velocity in between in between those 2 points.
We did find the average velocity there, but think way back to Algebra 1 and pre-algebra. We have 2 points,
Oh,
we subtracted the y's, we subtracted the x's, we found slope.
got it.
Okay? Now, this is where I want you guys some work with your group, okay? What we just found here was the slope from this point to this point. So we know that the slope of that line is, excuse me, a negative 25. All right? That gave us the average velocity. So with you and your partner, I've given you a number of other times here. I want you to use our formula to find out what the distance off the ground will be at that point. And then for each of those, I want you to find the slope between that point and F. Okay? Use F for all of the slopes. Okay? Because F is the point that we're actually looking for the instantaneous velocity at. Okay? So take a few minutes here and try that. Alright, so the values that we get here, when you plug in t is 0.5, what's the distance?
36.
36, and the slope is?
Is negative 33.02.
33.02. Okay, just call them out here. So for 0.8
29.76.
and negative,
37.84.
okay? At 1,
24 and negative 41.07.
okay?
Somebody else.
At 1.2,
60.96.
16.
16.
oh, 16.
I said 60.
You meant
You're getting
16.
16.
I meant 16.
Yeah, that's okay. And then the slope was negative 40,
4 point. I got 3.
44.3, okay? And then 1.3,
12.96.
Wait, what you got?
12.96.
I got 12.04.
Me too.
I'll double check.
what'd you guys get?
Well, I mean, he did just show it on the board, so.
Yeah, but like, shut up.
Was it right?
Yeah.
Okay. So negative, what was the slope?
46.
Negative 46,
Yeah.
okay? At 1.4,
8.64,
Way to go.
and then negative 47.75.
Okay, I know this one comes out to negative 50, and this was
Fell.
4? Okay. Alright, so notice here, you can see what's happening. You can see what's happening as time goes on. Notice in the first half a second it only fell 4 feet.
Yeah.
But in the last tenth of a second it fell over 4.5 feet.
What? It's
From 1.4 to 1.5. That's because the longer something falls, the faster it's falling. By the way, that's why it hurts more to fall from 10 feet than from 4 feet. Because you're hitting the ground at a much higher speed.
Let's try now.
Okay?
Okay.
It hurts more, you know? Force,
okay.
force is mass times acceleration.
I think Ken tested out.
Alright? So, now here's the thing. Each of those slopes is what? Negative, okay, which means we're falling down. That's good. But each of those is an approximation, or actually is the average velocity from, in the first case, a half a second until we get down to a foot off the ground. Okay? And then when we go to the 1 second, negative 41.07, the average velocity from the 24-foot mark down to the 1 foot mark is 41.07 feet per second. Okay? So all of those are average velocities. Which one do you think is going to be the closest to how fast it's actually going at a foot off the ground?
The 1.5. I don't know.
The one at 1.5?
Yeah.
Yeah, okay. That's right. Because the 1.5 is the closest point. Alright? So let's think about what we were just doing. We were finding the slope, you know, in the case of the last one, you had 1.5 minus 1, and you had 4 minus 1, and that ended up giving you a negative 1.56 minus 1.5 over 4 minus 1. No, 1 minus 4. Let's start that again. Okay, 1.56 minus 1.5 over 1 minus 4. And that gave you a negative 50. So you're finding the slope. Now, as we already surmised, the best approximation here is going to be the one that's the closest, has the point closest to it. So we're getting this point to be closer and closer and closer to the other point, right?
Yeah.
So what does that kind of bring to mind? If we're getting something closer and closer and closer to something. Limits. Aha.
I thought
Okay.
You owe.
So,
I taught him a new day and I was using it all the
You
time.
owe.
here's what we're doing, okay? Check this out. Let's take the same concept and understand what we're actually trying to find here. We're actually trying to find the derivative. This is one of the two pillars of calculus, okay? We've got derivatives and integrals that are both founded upon the limit. So the basic concept is this. The basic concept of a limit is exactly what we were just trying to find. We were trying to find exactly how fast something was going at a specific moment. Alright? So, in our case here, looking at this diagram, the moment we're looking at is what's known as a point of tangency. Okay? So we have that point of tangency. And this black line right here is called a tangent line. The derivative will give us the slope of this tangent line. Okay? So here's what we're going to do. we pick a random point on our function. I don't know how far away from the original function it is, but we're going to say that the x's have a difference of h units. All right, so if this is x, h could be positive or negative, so it doesn't matter if we're to the left or right. This is going to be x plus h. And then to find the y coordinate of that, we would take the function evaluated at f of x plus h. Okay? So question, what is the slope of that line?
Which one? Oh. So it'll be f of x plus h minus f of x over x plus h minus x. So what would that be? Could we simplify that at all? So it's x plus h minus x?
Yeah, what could we simplify the denominator to?
Just simply h.
Yeah, so guess what? The slope of any of these lines is going to be f of x plus h minus f of x over h. Now, we're moving this point closer and closer and closer to our point of tangency. What is happening to h as we do that? It's getting smaller and smaller and smaller and smaller, which means it is doing what?
Getting close to limit.
Getting closer to, what is h getting closer to?
The point of tangent.
The whole point of tangents.
The point is getting closer to the point of tangency, so what is this value of h getting? It's getting smaller and smaller and smaller and smaller.
Zero?
It's getting closer to
Yeah,
zero.
oh, because at that point, that's when it's zero, and that's when it's actually the limit.
And that's when it's actually undefined. So what are we gonna do here? We can't find it just using one point. So if we want h to get closer to zero, we're going to take the limit,
Yes, I got it.
okay? The limit. And guess what? That right there is the definition of a derivative. The limit as h approaches 0 of f of x plus h minus f of x all over h. We just derived what a derivative is and how to find it. Notice some notation here, okay? Notice some notation. If you're dealing with a function given as y equals something, okay, you can express the derivative of y with respect to x as dy over dx, like that. Okay? If you have a function f of x equals something, then you can use the notation f prime of x. Okay? So there's two kinds of notation here that are used, and they're both used the same amount, so just be familiar with both of them, okay? But that's the idea of a limit, okay? Don't write this part down, because we're going to actually do this on Monday and Tuesday, but I want to show you what this is used for, okay? Let's take the function that we were just working with, alright? F of x is 40 minus 16x squared. Okay? Now, if I wanted to find the limit as f of x plus h minus f of x over h as h approaches 0, then one thing I need to find is what f of x plus h is. So I have 40 minus 16 times x plus h squared. Okay? So I'm going to FOIL that. 40 minus 16 times x squared plus 2xh plus h squared. And I'm going to distribute the minus 16 as well. So 40 minus 16x squared minus 32x h minus 16h squared. Okay? So that's f of x plus h. So let's check this out. Let's see what happens. We have the limit as h approaches 0 of what we just found. So 40 minus 16x squared minus 32xh minus 16h squared minus the original function. Okay, so here's our f of x plus h. The original function is 40 minus 16x squared. And that's all over h. So now, let's look and see how we could simplify. How could we simplify the numerator here? Oh, what? What was your question?
Wait, where's the numerator?
I think it's a little laggy.
Oh, it's lagging. Sorry. It's not
That's what I
showing.
was wondering, you're like over
I can
H,
see it on my screen.
You're like over H, I'm like,
I got a little bit.
I'm not seeing it over H. Which way I was
All right. There it is. Okay. So, now, how are we going to simplify our numerator?
Can't do that. So distribute the negative in that second one and then just subtract, that's what I would do.
Okay, good. Yeah, so we'd have 40 minus the 40.
Right?
And
then
we-
you would have negative 16 squared plus 16x squared, so you're good there.
Yeah, so that cancels.
So you just left with.
So there we go. We have the limit as h approaches 0 of negative 32xh minus 16h squared over h. Now what do you notice that you can do?
Can't you?
You can factor, because there's gonna be an h, there's gonna be a hole whenever you plug in 0.
That's right, there's a hole at 0.
And how would you factor out an h though?
Well, just like this.
Oh, there's all h in all two terms,
So it's H minus
Just two
16, you're pulling, no,
Two terms.
you're pulling out
Two terms.
H
Okay? So we're pulling out an h
and the 16.
because, yeah, like you said, there's a hole at 0.
Right.
So
Did you do it and it's lagging again?
I did. It's lagging again. We'll cancel out those h's.
Oh, there it goes.
All right, so now look, we have something that we can simply evaluate plugging in 0 because this is a continuous thing here. So if I plug in 0, I just get my final answer of negative 32x. That is f prime of x.
And
Okay.
now what do we do?
Well, what point were we finding the velocity at? Or trying to approximate it at?
0.
It was when x equaled
30.
or t
1.5,
equals
1.56 or close.
1.56, yeah. It was when t equaled 1.56. So guess what? If I do f prime of the 1.56, that'll give me my instantaneous velocity. Okay? And that 1.56 times a negative 32
49.92.
is a negative 49.92 feet per second. Okay? So, our approximations were pretty close.
I say so.
We ended up with one that was a little above that because of rounding and stuff. But if we hadn't rounded, that last estimate would have been just slightly underneath as well. But here we have the exact. It's going exactly 49.92 feet per second downward. All right, so that's what we're going to try to find here. And by the way, this doesn't just work for motion. This can work for any type of function modeling a situation. We can find the rate of change using a derivative. Okay? So, that's our introduction to derivatives and a little bit of an exploration for you guys.